So now we'll deal with bounded monotonic sequences. So these are two terms, bounded and monotonic. Let's take it step by step. The first one is a sequence is bounded if for every m, that is a constant, is such that u of n is less than or equal to m, which means that the sequence is always less than some m, right? It means that m is the upper bound. You've already seen this in previous videos. Now, if that element m is such that u of n is always greater than or equal to m, then it is said that m is what bounded below. So we have the upper bound and the lower bound. These are terms you've already seen, right? And an upper bound m is called the least upper bound of a sequence if for every element greater than 0, there exists at least one term of the sequence greater than m minus e. So it means that the least upper bound is actually the smallest bound of the sequence, such that if you take any element of the sequence and subtract it from that least upper bound, right, the result you get is still in the sequence, right? I think maybe they show an example here. So, for example, this sequence, the sequence is the fraction between numerator 2n plus 1 denominator 2. Now, when you try to simplify, realize that this is what you get. And now they say the sequence is bounded below by 1 and bounded above by 4, right? Now, we can confidently say that the least upper bound is 3 and the greatest lower bound is 2. Why? Remember this part. Remember that this part will continually try to approach 0 the more you increase n. Exactly. So it means that the largest value of this part is what? 1. Right? When n is equal to 1. Right? So it means that the least upper bound is what? 3. Like the sequence will never exceed 3 because the more you try to increase the n, the next time you increase n, you get when you go to 2, you get 1 over 2, which is 0 0.5. 0 0.5 plus 2 is what? 2.5. It is less than 3. So you realize that if you try doing any more increments, you get values lesser and lesser than 3. Now the greatest lower bound is 2. And what we are saying is that this sequence would continually decrease, right? Because the more you try to increase n, you'll be getting values which are more closer to 2, right? So for example, the first term will be 2 plus 1 over 1, which is 3. The second term will be 2 plus 1 over 2, which is what? 2.5. The third term will be what? 2 plus 1 over 3, which is what? 2.33. You realize they are getting closer and closer to 2. Now, you realize that the more and more you increase, as n approaches infinity, you realize that then you are getting to 2, right? So the greatest lower bound is 2. That's the least element of the sequence would be 2. Now, a sequence is said to be monotonic increasing or non-decreasing if the previous term is always less than the next term, right? So this is how they say it in mathematics instead of putting it in English, right? Now you realize that if it is vice versa, such that the previous term, the next term is always less than the previous term, then we say the sequence is what? Monotonic decreasing, right? So this is a monotonic increasing, that's a monotonic decreasing. There's not much to say about it. So what can you say about this sequence? Is it monotonic increasing or monotonic decreasing? Well, it's a monotonic decreasing sequence, right? Because the first term will be 3, the next one will be around 2.5, and you keep on. So you keep on decreasing, right? Now, you have to show this, and these are usually proofs that you probably may be asked to show. So let's take a few of them, quickly go through and see how we can try our hands on them. So the first one is we are given this sequence. The sequence is such that it's equal to the fraction to numerator n plus 1 over n. And now you want to show whether it is a monotonic decreasing sequence, right? Now you remember the case for a monotonic decreasing sequence. Whether it is monotonic decreasing or monotonic increasing, you'll still have to find this expression. U of n plus 1 minus what? U of n, right? Now, how do you find U of n plus 1? see, u of n is what? N plus 1 over n. So u of n plus 1 means that anywhere you see n, put n plus 1 there. You realize that when you substitute n plus 1 for this n, you get for the numerator n plus 1 plus 1, right? Now when you do the same thing for the denominator, you get what? Only n plus 1 because there's only one n in the numerator. So in the result, you get n plus 2 in the numerator and n plus 1 in the denominator. And that's what you see here, right? That's what you see there. So you just substitute n plus 1 for everywhere you see n in that expression to get the u of n plus 1. Is not difficult. Now u of n was already given, so that's what you see here. So we don't change it, right? But I want to find their difference. So yes, this is u of n plus 1 minus this u of n. Then now you simplify. I strongly believe you should be able to do this. Basic algebra, but I mean, for the sake of being thorough, let's quickly go through. So what you usually do is that since they are not numbers, you can't really find LCM, right? So you just multiply the two of them as the LCM. Now n plus 1 divides the LCM, n into brackets n plus 1 n times, right? So you realize that the numerator n plus 2 multiplied by n minus, realize that this one n divides the denominator with n plus 1 times. So the n plus 1 will be multiplied by n plus 1, right? So this n plus 1 will multiply by this n plus 1 in the numerator. I'm very sure you could do this. Then we end up with an algebraic expression which we have to simplify. So when you expand the bracket, this is what you get. Then finally, you realize that you get what? Negative 1 over n into bracket n plus 1. Right, now, what does this expression tell you? It tells you that, see, always, so far as n is a real number, n is a natural number, you will always get a value less than 0 because the numerator is negative 1. So it means that the value, no matter the value you get here, to be negative, right? So it means that the value is always less than 0. Now, if the value is always less than 0, what does it tell you about this expression? It tells you that this u of n is greater than what? This u of n plus 1. Remember, very long ago, we were treating trichotomy and transitivity. Yes, so these are the applications, right? You realize that it's quite basic, but you are just applying it here. So realize that it means that what if I'm subtracting two numbers and I'm getting a negative answer, then it means that the second number was larger than the first number, right? This is just pure logic. And so you realize that it means that this sequence is monotonically what? Decreasing, right? Because the next term is always less than what? The previous term. And that's what you see. And here, yes, so they just stated it, and that's what you see. So it's as simple as that to state that the sequence is monotonically decreasing or increasing. Now the next question was, we have to show that this is a bounded sequence, right? So let's go through the step. Now, one way you can do this is you just start listing the terms of the sequence, right? And this is, should I say, not a very foolproof way of doing it, but I mean, once it works, sometimes you can go ahead. But usually, most lectures will require you to show the mathematics behind, so we will probably do that. So you start stating some few terms of the sequence. So when n is equal to 1, you realize that you get 2. When it's equal to 2, you get 3, and you continue. But one thing you realize that this sequence is continually decreasing. Approaching what value? It's approaching 1. It's decreasing to approach 1. So the sequence is bounded above by what? By 3, because the largest number you can get, right, is 3 from there. Is 2, but the largest number you can get is around 2, but because I mean we are just trying to be safer side, because 3 is not in the set, then we use 3. So this is how you may probably prove it. Remember that you can go ahead and do n over n plus 1 over n, right? For this expression. Now this gives you 1 plus 1 over n, right? Then this expression, right, is 1 over n. Now n starts from 1, 2, 3 going. Now you realize that if n is equal to 1, you get 2, right? But if n is equal to 2, you get what? 1 plus 0.5, because 1 over 2 is 0.5. So 1 plus 0.5. So the next term will have what? 1.5. If n is equal to 3, you would have gotten what? 1 plus 1 over 3, which is around 1.333, right? Now you realize that you are continually decreasing, right? So realize that the maximum element of the set will be 2, right? However, because 2 is a member of the set, then if we are bounding it above, then we say the next greater number, so we say 3. Then the least element of the set will be 1, right? This sequence will never get to anything less than 1, right? Because if n approaches infinity, then this term will approach 0, right? So you realize that it gets only 1. However, because 1 will end up being a member of the set at infinity, then we can say it's bounded below by what? 0. Now, there is a theorem, and it states that every bounded monotonic sequence has a limit, right? Every bounded monotonic sequence has a limit. It doesn't matter when if it is monotonically increasing, then it means that it has a least lower bound. If it's monotonically decreasing, then it means it has a greatest upper bound. Something like that. So you can test it. Probably we'll see examples on that, working that, so that we practice with our hands. So an example is this, where you have use the above theorem to establish that the sequence n over n plus 1 has a limit, right? Prove that the limit as the sequence approaches infinity is 1. Now, what they try to do the same old trick. First, you realize that you have to do two things. You have to show that it's a monotonic sequence. You have to show that it is bounded, right? If those two hold, then it means it has a limit. So that's what you are supposed to do, right? Using the theory. So the first thing they are trying to do is that they are trying to show that it's a monotonic sequence, and we've already gone through steps, right, to show that sequence is is a monotonic sequence. You would subtract the previous term from the if you subtract the current term from the previous term, then you solve. Right now, you realize that this sequence is monotonically increasing, right? Because you would always get a value greater than 0, greater than or equal to 0. Now, to prove that, so that shows it's monotonic, right? And these are the steps. I hope you can go through them. Then, to prove that the sequence has a limit of the sequence has a limit of 1, then it means that we have to show it numerically, right? So you realize that we use the same limit point theorem. What do? We subtract the limit from the sequence, right? Because if the sequence has a limit of 1, that means that once you subtract it from it, then it will be always less than a delta. So once we subtract 1 from this expression, taking the positive version, right? Because remember the limit point theorem, you have to take the positive version. So taking the positive version, realize that we get what an expression 1 over what n plus 1, and now this expression is always less than 1 for every n greater than or equal to 0, right? So it shows that the sequence has a limit point of 1, and that's as basic as that. There are other ways you could have proven it, right? One very simple way could have been, instead of writing n over n plus 1, you could have said this is the same as when you divide the numerator and denominator by n, you get this 1 over n, right? Now n cancels n cancels n, so you get 1 over 1 plus 1 over n, right? Now we are saying that n approaches infinity. Now if you put infinity, you realize that this expression goes to 0, right? So you realize that now the limit to be what? 1, right? To be 1 over 1 plus 0, which is 1. Right? Now this is another way, but this is directly from the Bolzano-Weierstrass theorem, and probably they may require you to use that theorem. So yes, and that brings us to the end of this video. Thank you very much, and you can continue to